Alright guys, welcome back. Today we're going to be furthering our understanding in instantaneous rate of change, and specifically we're going to be using graphs. So as you can see, we got some examples for us here to lead us up, and then obviously we're going to be doing all of these explorations, and let's see. So we're going to be using decimals. As you already can tell, I showed it for a quick second. Yeah, let's go ahead and just, start. So first of all, we have this. In the previous lesson, we used numerical and algebraic techniques to estimate instantaneous rates of change. Now, graphically, you've seen that the average rate of change is equivalent to the slope of a secant line that passes through 2 points on the graph of a function. So last lesson, I also briefly mentioned the concept of a tangent line, and this is what we're going to be looking at this today. So, first of all, let's have this example. How can you use slopes of secant lines to estimate the instantaneous rates of change? So last lesson, I showed you guys that as we could have this graph, and by having a smaller and smaller and smaller interval, the secant line will kind of sort of be equal to this. It will be very similar to the original line in a certain way. But obviously, let's just do this. So we're entering the function f of x equals to x squared into a equation editor of our graphing calculator. We're going to graph it, sketch it, do whatever we want. And on our graph, we're going to be drawing a secant line that passes through the points 1, f of 1, and 3, f of 3. So let's go ahead and do that. So f of x is equal to x squared. Makes sense. Okay, sure. Sounds good. So we're going to be drawing a secant line. So specifically, we're going to have a set of dots. So 1 and f of 1. Label that. And we're going to have 3, 3, f of 3. So we have these 2 points. We can't really get a point to connect them, which is kind of bad. But that's fine. Is there a way to connect this? No, we actually can't. So that's fine. So anyways, let's calculate the slope of the secant line. So we have this. Calculate the slope of the secant line, copy the table, and record the slope. Calculate and record the slope of. So we don't really need, to have an actual line here, but you could draw this. Definitely go ahead and sketch this. All we have to do is just do dy over dx, right? So the change in y is 9 minus 1, so 8 over the change in x is just 2, so now equal to 4. So slope is equal to 4. So, how are we gonna do this? Let's just let me just write it onto this. So 4, and then 1 f of 1 and 2 f of 2. Let's go ahead and do that. So 1 f of 1 and 2 f of 2. So we'll have the change in x being 3, and the change in y being 3, change in x being 1. So 3 over 1, that's just 3. So slope is it's 3. So let me just 3. Wow, I can't even write anymore. Okay, that's fine. So let me move this. Why don't I just move this? Moving this. So now I can just write next to it. So we'll have 4. We'll have 3. Then now is when we actually need a calculator. So let's go ahead and check f 1.5 and f 1.5. So we have 1.5 and 2.25. Now our initial point is also 1f1. So our change in y is 1.25 over 0.5. So 1.25 over 1.5 minus 1. So that's 2.5. So we'll have a slope of 2.5. Now let's do 1.1. What's going on? Oh, I forgot to decimalize this. Okay. So we'll have 1.21. The change in y is 1.21 minus 1. And all of this is over 1.1 minus 1. So the slope is now 2.1. And then finally, let's do 1.01, which is even smaller. So 1.01. So we'll have that really, really small change. So 1.0201 minus 1 over 1.01 minus 1. So we'll have 2.01. And notice that, so this is, let's say this is our right side of our graph. And then from 1, for our first point with the slope of 4, we'll have something like this. And then for our point with 1f of 1 and 2f of 2, we'll have something like this. Notice our interval is getting smaller, and our line that we draw is closer and closer to the graph. And finally, 1.5 will give you something like this, right? Very similar to the graph now. And then 1.1 will be this very small area. And now you're looking like and be like, wow, that's almost exactly the same as the graph. And finally, 1.01, that's like exactly mimicking the graph. So here, when we have such a small interval, we can just basically conclude that, hey, look, our interval is so small that when we draw a secant line, it's basically the same as how the original graph is. And so this is how we estimate the instantaneous rate of change. Okay, let's go ahead and do D. Create a formula calculating the slope of any secant line that passes through point 1 f of 1 and the general point x f of x. So we don't really need a formula. All we need is the slope. We don't really need any new formulas. All we had before is our slope formula. So using slope formula for a slope of any secant line that passes through 1 f of 1 and x f of x, we have slope equal to top will be f of x minus f of 1, and this is all over x minus 1. Okay, so we have our general formula, and we want to input this into our y1 equation calculator. So let's go ahead and do that. So let's do f of x. Yeah. This is weird. It won't let me have everything over x minus 1. So over there. Okay, there we go. So we will have f of x minus f of 1 over x minus 1. And then we enter this formula. So set the table set featuring our graph. Okay, so we can't really do this because we don't have our graphing calculator. Confirm that the first slope that we calculate in part C is correct by entering x equals to 3 into my graphing calculator, which I don't have, but g of x equal to, and then g of 3 is equal to 4. So we verified our formula. We're like, okay, that's fine. And let's check g of 2. G of 2. Okay, it's equal to 3. So it's exactly what we have here, right? That's pretty cool. Anyway, so we already confirmed this. Now let's go ahead and move on to this part. So on your sketch, draw another secant line that passes through which we already have, supposedly. Calculate the slope by entering x equal to 2. And though we already compared, so g of 2, that's equal to 3. It's the same as our table. Draw and calculate 3 other secant lines. So you're supposed to draw it on your own, while I will just verify the calculation for you guys. So g of 1, g of 1.0, sorry, 1.5, g of 1.5, g of 1.1, and g of 1.01. Okay, so we notice that we will have 2.5, 2.1, 2.01, 2.5, 2.1, 2.01. So it's all the same as what we have as calculated on the table. So we examine our sketch in our table of secant slope, describe what happens to each secant line in our sketch. So we just did a quick sketch over here. So we can see that originally this is a huge gap, and we drew a secant line that doesn't really match the graph. And then we close the gap from 1 to 2. Sorry, 1 to 2. And then we close the gap a little bit. We see that our secant line has gotten a little bit closer to the graph. And then we zoomed in again to 1.5, and we look like, okay, this is very close to the graph. And then 1.1, even closer. And finally 1.01, we're like, wow, that's almost the exact same thing as the graph. Right? So we can estimate the slope of the tangent line to the curve f of x equals to x squared at point 1 f of 1. by examining the trend so we can estimate. So we already got pretty close. We got to G 1.01. What if we draw a tangent line secant line that's so small? What if we go from 1 to 1.00000001? So essentially, what we're gonna have is that in this part, in this area, so in this area of x equal to 1 is right here. X equals to 1 right here. We're gonna zoom in. So this is a zoomed in picture. We're gonna have a zoom in where this is x equals to 1, and this is x. Sorry, we're gonna zoom in so much to the point where it's gonna almost look like a straight line. It's gonna almost look at a straight line. And how much do we need to zoom? Well, we don't really know, but we can go really small. So let's say this part is x equal to 1.00000001. Okay, so 5 zeros. Because that's pretty small, right? So let's see. Let's see if our slope gets any more accurate. So 1.000001. Wow, so it's 2.000001. And that basically rounds to 2. So what does that mean? It means that by estimating the slope of the tangent line, we can estimate that the slope of the tangent line is 2 at 1 f of 1. So we're going to repeat the process with whatever this is. So right here is that instead of using points on the right of f of x, we're using points on the left of f of x. So we already have a formula that can calculate this for us. So let's go ahead and calculate. So g of negative 1, does it work? G of negative 1, and then g of 0, and then g of 0 0.5, g of 0 0.9, g of 0.99, and finally, let's get even closer. So 0.9999999. We notice that at one point, this rounds to 2. This fluctuates and rounds to 2. And decimals, this is the fun thing about decimals right here. So when you enter so many digits, this is basically 2. The slope is basically 2. They round it for us. It's basically 2. Because we got so precise. We have how many 9s? We have a lot. We have so much 9 here. With not so much 9s here, that essentially decimals rounds this because it's so close to 2. Maybe it's close to 2 by just one of 1 billion of a decimal place, so that our decimal calculators rounded it to 2. So it looks like that no matter which way we go, we could stay on the right of the graph and say we can draw let's say we have this graph here, which we do. So let me draw another graph on the right. So let's say we have this graph here. Right, we can use this point, we can use everything here to estimate the slope here, right? Or we could use everything on the left of it to also estimate the slope. It doesn't matter which side we use. So verify our estimates. So that equals 1. Okay, so I don't really need to do this. But let's go ahead and look at this. So with 2 other functions of your choice. So you guys can do one function. I will be particularly doing the sinusoidal function because the sinusoidal function is very interesting. It's pretty cool. So let me just have the sinusoidal function up. Yeah, let me have the sinusoidal function up. So let's do sine of x. Why not? Just sine of x looks pretty cool. So we will see that because our sine of x is a sinusoidal function, it repeats. Essentially, what's going to happen to our graph is that it also repeats. So let's go ahead and see. So why don't we estimate the slope at the slope at, let's say, what's a good slope? Let's do 180 degrees, or pi over 2. No, actually no, it's just pi. Yeah, 3.14. So let's see, what's the slope of G 3.14? Right, since this is technically still gonna work. Essentially, it's just gonna be a little more complicated because we're going to be in radians. Let's go ahead and do that. So what happens to the slope of the secant point? So let's do yeah. So um I actually don't really understand how the metric here works. So let's just do 1.5 instead. So G, let's pick a value from 2, and then G of 1.6, and then G of 1.51, and then G of 1.500001, and then G of 1.50000001. And then notice that these two has barely any change, and then we can conclude that the slope at 1.5 for a sinusoidal function on whatever metric that Desmos is using, we can conclude that the slope at 1.5 is basically 0.312, because the change here is so minimal. It's changing by what? 1, 2, 3, 4, 5, 6. It's changing on the 6th decimal place. That's really, really slim of a choice. So we can say that the slope of the secant line gets closer, closer, and closer to the slope of the tangent line when x equals to 1. Oh, okay. So how is estimating the slope of a tangent line like estimating the instantaneous rate of change? Well, because our line, I'll draw a line here instead. So because we have this sinusoidal, let's not use the sinusoidal function. It's kind of complicated to draw. Let's just use our quadratic. Because we got so close to our point of that we want to focus on. So let's say our point was x equal to 1. So essentially this is going to be our, wow, it doesn't let me do anything. So this is our point right here. This is our point in there. That's x equals to 1. So that's x equals to 1. And then essentially, because we're going to have so many secant lines, and then our secant line is going to slowly have a smaller gap. So this is going to be a set of secant lines that we're going to draw. So I'm going to draw our secant lines here. So we're going to go from really broad to less broad to less broad to less broad to less and less broad to the point where the slope of our secant line is going to be the same as the slope of our tangent line. And by estimating finally our very last secant line, the slope of our very last secant line, we can basically say, because the secant line is so close, like a tangent line, and a tangent line only touches the graph at one point, by the way. So because this slope is so close to the slope of a tangent line, we can basically conclude that this is the tangent line, and this is the slope of our focal point on whatever function that we're using. Okay, this is just a quick exploration, and it's interesting to use decimals sometimes. But let's go ahead and look at the summary of today's lesson. Okay, so the slope of the secant line is equivalent to the average rate of change over the interval defined by the x-coordinates of the 2 points that are used to define the secant line. The slope of a tangent line at a point on the graph is equivalent to the instantaneous rate of change of the function at this point. So what do we need to know? The slope of a tangent line cannot be calculated directly from the slope formula, because the coordinates of only one point is known, right? The tangent line only touches the graph at one point. However, the slope can be estimated by calculating the slope of a series of secant lines that go through a fixed point of tangency P and points that get closer and closer and closer to this point. So basically P plus 1, P plus 0.1, P plus 0.01, and then P plus 0.0001. So yeah, so we can see, and this is basically telling us we can do both from the left and from the right. So as Q approaches P from the left, so this is Q1, Q2, Q3, and then we can see Q3 is pretty close to P, it's much closer. The slope of QP increases and approaches the slope of the tangent line that goes through the point P. And over here we can see on the right is the same thing. As Q approaches P from the right, the slope of QP decreases and approaches the slope of the tangent line that passes through point P. Okay, that is it for our lesson. There's some examples for you to do on a graphing calculator, which you can use decimals on page 91, 92 in your textbook. Okay, I hope you enjoy the lessons, and next lesson we're gonna get to the rate of change using a graphical model.